Welcome to Required Practical 2. This practical is on the topic of interference, both double slit diffraction interference and diffraction gratings. So from the double slit diffraction, you should be aware of this equation, where the fringe spacing is equal to the wavelength of the light multiplied by the distance to the screen divided by the slit separation. It's more usual during this practical to be discussing this version of the equation, which is just this one rearranged, because most of the time you'll be calculating the wavelength of the light. So what will typically happen in this experiment is that you will have your laser set up so that it's shining on a piece of card with two very, very small slits in it. And I'm talking about so small that the separation between them is less than a millimeter. That's pretty typical for this experiment. And then you'll be shining that laser light onto a screen. So the light will be coming out from the laser, landing across the double slits, and then forming fringes on the screen over here. So the light is coming out and hitting those fringes. Okay. You'll notice that the fringes formed are quite wide, and one of the things that you'll need to be measuring in this experiment is the fringe separation. So it's up to you whether or not you measure the distance between the two very wide fringes, and you'll have to go from the very center to the very center, or you could do it a different way and measure the distance between the dark areas. And remember that the dark areas are going to be narrower, so it may be easier to identify the center, and it's up to you what you do there. So the way that this experiment can work is essentially there are two values here. We've got four variables. Two of them are fixed by the equipment that you have available at your school. And depending upon the budget of your department, you may only have one laser and one double slit. So that fixes this value here and this value here. Those essentially are fixed by the availability of the equipment in your department. So the only values that you can really change are the fringe separation and the distance. And the fringe separation is dependent on the distance. So this has gone from 4 variables essentially down to 2. So the distance to the screen, this value here, this is now your independent variable. This is the only one that you can really change, assuming, of course, that your department doesn't have infinite money and a whole range of lasers for you to use. So this is the independent variable. This is the one that you can change. And then the fringe spacing depends on that distance. And what you'll do is you'll collect that data and then you'll plot a graph. If we tweak this formula one more time, then we can rewrite it like this. And therefore, if we plot the fringe spacing against the distance to the screen on a graph, then this will be our gradient. It will be a straight line, and we know that because the gradient is going to be this, which is equal to this. This value here is fixed because it's the wavelength of the laser, and this value is fixed because the slit separation isn't changing halfway through the experiment. We're keeping these two pieces of equipment the same, so these two numbers are staying the same. Therefore, that's a constant, and this will be a constant. So we're going to have a straight line graph. And the gradient of that graph, remember, y equals mx plus c. That's the equation of a straight line graph. The gradient of the graph is going to be equal to the wavelength divided by the slit separation. What your teacher may do is ask you to calculate the wavelength. And what they will have done is put a sticker over that information where it was printed on the laser and ask you to calculate the missing value. You'll be able to use the slit separation printed on the card over here in order to do that. Once you have your value, what they'll probably do is take away the sticker and show you the manufacturer's value. So if, for example, the wavelength was 500 nanometers, it will have a manufacturing tolerance of, say, 5%. And you'll need to compare your answer to this printed value. And if your answer, for example, let's say you had 510 nanometers, but your error was something like 20 plus or minus 23%, if this range of answers overlaps with this range of answers, then you have a successful experiment. If your teacher goes on to ask you to do another experiment using this setup, then what they might do is this. Before revealing the manufacturer's value, what they might do is ask you to use a new double slit and use your calculated value for the wavelength to then calculate the double slit. So what we have now is we have the percentage error in your answer being fed into another calculation where you'll have a percentage error of this answer, and then they'll have the big reveal of this one, and you'll be able to analyze your errors. It can get quite interesting doing that. Alternatively, what they might do is ask you to calculate the slit separation by hiding that value from you, and you'll be able to see the manufacturer's tolerance. So you'll have access to that information and be able to take that value through into your error for calculating the slit separation. In the double slit experiment, you have two slits, and you have fringes that are quite wide, and you have narrow, dark areas. The fringes are also quite close together. If you were to add more and more slits, then what happens to the fringes is that they get narrower and they get further apart, and that makes it easier to take practical readings. So the diffraction grating is just a fancy way of saying that instead of having two slits, we have thousands. It's a grating instead of just two slits. It's easier to show this experiment vertically. So here's our laser, here's our diffraction grating, and then here's our screen down below. If we shine our laser onto a diffraction grating, what happens is that you get a central fringe, and what you'll see on the screen is a dot, and then you'll get other fringes that spread out like this, and what you will see on the screen are just individual dots. Okay, that's better. We should have equal distances between those, and now we do. The equation for a diffraction grating is n lambda equals d sine theta. N is the number of the fringe, and the one that's in the center, the one that's directly ahead of the laser, is n equals 0, and then the first one that you come to after that is n equals 1, and that works in both directions as well. And then the next one would be n equals 2, 3, 4, etc. So that's the number of the fringe. We've got the wavelength of the light again. D is the diffraction grating equivalent of the double slits S, the separation between the slits. Sine theta, that's the separation of the slits, and theta is that angle there, the one between the straight ahead direction and the fringe that you're looking at. So in order to calculate this, you're going to need to do some trigonometry. You're going to need to measure this distance here, and you're going to need to measure this distance here, and you're going to need to work out that angle. And again, what your teacher might do is they might hide the value of the laser from you, or they might hide the value of the diffraction grating, ask you to use your calculated version of this to then do another calculation with another missing value so that your percentage errors are combined together, and you need to analyze it very carefully using the skills that you've already developed.